All right, hi everybody. We're back once again with the annual walkthrough of Regents. This is last June's test. This is the June 2024 test. You did this on Friday in school, hopefully. If not, that's kind of an issue because you were told to do so, but whatever. I'm going to go through it one question at a time. I'm going to plan to break it up into 3 separate videos for one each of the 2 multiple choice parts and then one for the short answers. And hopefully you can actually hear me, the microphone I'm not quite confident in, but we're going to make the best of this and see how it goes. So, number 1, which description of the atom is based on the results of the gold foil experiment in the early 1900s? If you remember how Rutherford's gold foil experiment went, he had a bunch of gold, just a piece of gold and foil, obviously, it's based on the name, and shot alpha particles at it. He shot the alpha particles, and most of them went straight through the other side to show up on a detector, but some bounced off, some kind of glanced sideways, some deflect in a different direction, and his big takeaway from that was really twofold, that there are dense, positively charged, really tiny centers of the atoms that we now know as the nucleus, and that atoms are mostly empty space. So most alpha particles went straight through because they just, by dumb luck, were not actually hitting anything, but every once in a while, you would have something hit right into the nucleus of an atom and bounce off another direction. So going through this, if you don't remember how this works, try to get rid of any answers that don't really make any sense. Atoms are small, dense, indivisible spheres. That's what they thought originally, but that really wasn't anything we got from this experiment. Atoms are composed of protons, electrons, and neutrons. True, but that again was not really anything we got from this experiment. Atoms have electrons, wave-like properties. That was much later. That was something that was figured out in a different experiment entirely. And here's your answer right here. Atoms have small, dense, positively charged nuclei, and they are mostly empty space. Only part of that is in this answer. Number 2, according to the electron cloud model, which term is defined as the most probable location of an electron in an atom? This is just a straight definition question. You just have to know what this word orbital means, and that is that. That is the definition of an orbital. We don't know exactly where the electrons are, but at any given time, we're really likely to find them in this place that we call orbitals. Number 3, which change occurs when an electron returns from a higher energy state to a lower energy state? So we have electrons in those rings, in those energy levels, and if an electron is here, it can absorb some energy from outside. It might be light, it might be heat, whatever, electricity. It jumps temporarily up to a higher energy level, and then it gives that energy right back again as light as it returns to where it came from. So it says returns from a higher energy state to a lower energy state. So going through our choices here, you're not making any kind of new compound, so we can cross off choices 1 and 2. And then the last 2 say a specific amount of energy is absorbed or emitted. Well, when it returns to a lower energy level, energy is going to be emitted or released. So that is choice 4. Question 4. Which phrase describes the different isotopes of an element? If you don't remember what the word isotope means, it's got to be something specific, right? Why would they ask you this question? So looking at all our choices here, it's one of those questions where the answers have kind of combinations of things. Every answer choice here says either same number of electrons or same number of protons, or same number of neutrons, and then different number of protons, neutrons, electrons. So some combination of something the same, something different, or maybe something like that. Well, if everything's the same, why would they even bother asking, right? So if any choice is something like same number of this and same number of that, I'm just going to ignore that right off the bat. I don't see that here. It looks like every choice is same number of one thing and different number of something else. So because the question rather says different isotopes of an element, I know it's got to be the same element. And hopefully you remember that the number of protons is what makes an element what it is. So I'm going to go with same number of protons. I'm going to look for that. So like this choice right here, number 3 says same number of protons. Same number of protons here in number 2. And I'm also going to notice that if that same thing is there twice, that's probably a pretty good indicator it's going to be in the right answer. They're giving you like kind of a little distractor or an option answer. So I'm going to say that's probably one of the 2 choices. And different number of what? Well, it's going to be neutrons. Different number of neutrons is what makes these things different. They're the same element, but different number of neutrons gives them different masses, gives them different weights. So they're slightly different massed versions of each other, like the carbon-14, carbon-13, 12, all these different versions like that. Those are what isotopes are. So if you remember what the isotope means, great. That's kind of what you need to do to answer this question, but you could sort of try to logic it out otherwise and give yourself a pretty good chance to guess. Number 5. Which statement describes a chemical property of sodium? Chemical property is essentially saying this is how something is going to react, this is how it's able to change. So we have to look for some kind of answer like that. Silver in color, that's just a physical property. That's not going to be a chemical thing. As a density of this, it has an atomic radius and it's highly reactive. As soon as I see that word reactive, that's what I'm looking for. It tells me that's how it's going to behave, that's how it's going to interact with something else, and choice 4 then is going to be my answer. 6. Oxygen can exist as diatomic oxygen gas, O2, or ozone, O3. These two forms of oxygen have, and then again, the choices all say either the same or different structures and the same or different properties. Well, you don't necessarily need to know anything about this. O2 and O3, you know that they're both oxygen forms, and one has 2 oxygens, one has 3 oxygens, but you probably really don't know anything about these things, much of anything. They're different. That's what you gotta know. They're 2 totally different things, O2 and O3. If you just picture the structure of these things, one's going to have 2 oxygens linked together, one's going to have 3 oxygens linked together. So right away, you know it's going to be some kind of different shape, some kind of different structure. So I'm going to cross off anything that says it has the same structure. Now we're down to 2 choices. So different structures and different properties, or different structures and the same properties. Again, it's different things, so we have to assume they're going to behave differently. So different properties is what I'm looking for. So I'm going to get rid of the same here, I'm going to get rid of the same here, and all we're left with is choice number 2. Number 7, which formula contains a polyatomic ion? Polyatomic ions are those things where it's sort of bigger chunks of elements, 2 or 3 elements at a time. We could either go to the polyatomic ion chart on table E. That's the inside front cover of your reference table. So you could either look right here on table E and just kind of match up which of these ions on this chart are actually in this question. Or if you just notice, look at what the choices look like. 2 different elements, K and S. 2 different elements, Al and O. 2 different elements, Al and Br. Choice 1, KCN, that's the only option where there's more than 2 elements. So it can't just be 2 elements, something in there is an ion. So right off the bat, that's our choice. If you want to double check, you can go look for that on this chart, and you'll notice right there is Cn. So it was K as the element potassium in the metal, paired up with Cn, cyanide, the ion, and that's your option right there. This is just a metal and non-metal. This is just a metal with a non-metal. This is just a metal with a non-metal. But this one right here, choice 1, that's the one that has a polyatomic ion. Number 8. What information about C4H10 can be determined from its structural formula, so what it looks like, but not determined from its molecular formula? So what can we not tell by just looking at this formula here of C4H10, but we would be able to tell by looking at like the physical, the picture of it, the Lewis structure, the structure of it. Physical state, I mean, by here we can't tell exactly what it is. It doesn't say anything about solid, liquid, or gas. It doesn't have the little S or L or G in parentheses that we see sometimes. Molar mass, we could see how heavy this thing is, right? We could add up what 4 carbons and 10 hydrogens weigh. That really would make a difference. Ratio of different atoms, we can tell that from the formula. We can see there's 4 carbons and 10 hydrogens, that works. But the arrangement of the atoms is something we don't know. We don't have a picture, we don't know what this thing looks like, we don't know what its structure or shape is. So that's something we'll be able to tell from the structural formula, but we can't tell from just this molecular formula. That's not going to tell us one bit what the arrangement is. If we had 4 carbons and 10 hydrogens, we could potentially put them together in a couple different ways. So we would need to actually have a picture at that point. We can't tell from just this. Number 9. Which quantity is conserved in all chemical reactions? In all chemical reactions, we have to have charge conserved. If you're losing electrons, you have to gain electrons. If something is a positive charge over here, you have to have a negative charge somewhere else. You have to have charge conserved. That's, again, just kind of a definition to know. You don't always have to have the same volume. Things can expand, things can shrink down. Moles, you have the same material, but you may combine things where like 2 moles of oxygen and 1 mole of something else combine now into a mole of something that's different. Density might change, but charge has to stay the same. You can't lose or gain electrons without also losing or gaining electrons somewhere else. Page 2. What do the coefficients in a balanced chemical equation indicate about the substances in the equation? So remember, coefficients are those big numbers that go in front of formulas in an equation. So if I turn to table I here, these big numbers in front of the coefficients. That 2 of the CH3OH, that 2 is a coefficient. The 3 here in front of the carbon dioxide, that 3 is a coefficient. And it's telling you how many of the entire compound, how many of the entire molecule you have. So this means if we take 1 of these C3H8s and 5 of the O2s, we can react them together to give us 3 of the carbon dioxides and 4 of the H2Os. On a really micro scale, if we were only using 1 molecule or 5 molecules each, that would be great. But on a more realistic real world scale, they mean moles. So 1 mole of C3H8 and 5 moles of O2 give us 3 moles of carbon dioxide and 4 moles of H2O. So let's try to find if we can have a answer that looks kind of like that, and we do. We have mole ratios. That is our answer right there, choice 2. At STP, which substance has metallic bonding? Metallic bonding just means you're talking about a piece of metal. That's it. Metallic bonding is what's going on inside a piece of metal. Electrons are being passed around. They're kind of playing hot potato. Look for the metal, and titanium right here is the metal. If you don't remember how that works, hopefully you're just looking at this and saying, well, metallic bonding, maybe that's something to do with metal. And when you look at these things, argon is a noble gas. That's a nonmetal. Sulfur dioxide, sulfur, and oxygen are both nonmetals. That's probably not going to be an answer. Choice 2, you'd say, well, barium's a metal, chlorine's not. Maybe that might make sense. But titanium is just the only piece of metal. That's what we're looking for. It's just metal. Titanium's your answer. Number 12, how many pairs of electrons are shared between the nitrogen atoms in a molecule of N2? It would really help if you remember what nitrogen looks like. I'm going to give you some structures. I think they're already in Schoology of some common pictures of things, some common Lewis structures that show up a lot. If you remember that oxygen, 2 oxygens pair up like this with a double bond, that's great. Well, nitrogen pairs up with a triple bond like this. If you needed to, you could always go look up the electrons and draw it. But if you remember that 2 nitrogens pair up with 3 bonds, that's great. And then it says how many pairs of electrons, so it's just 3. Be careful of these questions. Sometimes they'll say how many electrons, in which case it would have been 2 electrons per bond. Well, 6 is not an option here, so it's kind of nice of them, whoever wrote this question, they didn't give you that as a fake distractor answer. It just says how many pairs of electrons. So 1 pair, 2nd pair, a 3rd pair, that's 3 pairs of electrons. That's your answer. 13. Which formula represents a molecule with an asymmetrical distribution of charge? Again, if you remember what some things look like, great, but just draw yourself little pictures if you have to. You don't have to go crazy. You don't have to get too complicated, too detail-oriented. Just what would these things look like? It says which one's going to be asymmetrical, so it's not going to be balanced. It's going to be, sort of lopsided maybe. Cl2, it's just 2 of the chlorines, so it's going to look roughly something like that. I'm not worrying about drawing the electrons, but I know it's 2 of the same thing with a bond between them. That's going to be symmetrical. Both sides are going to be the same as the other. CH4, it's a carbon with 4 H's. So I'm going to draw a carbon with just 4 H's. And again, I don't have to worry about counting electrons, don't have to worry about anything else. I know it's just going to look something roughly like that. And that, again, looks pretty symmetrical to me. Every side is the same, nothing's different. Water, you may be tempted to draw water with an O in the middle and an H on each side, very kind of straight like this. But hopefully remember that's not exactly what water looks like. Water actually has that sort of bent shape. And if you don't remember that, just go get a drink. It's on the water fountains everywhere in the building. That's what water looks like. So water is never symmetrical. Water is always a polar molecule. That's not going to be your answer. CO2, I'm sorry, which one? It does say, asymmetrical. That's what you're looking for. H2O. Asymmetrical, that's what you're looking for. CO2 is where you have carbon in the middle with oxygens on each side. That's also pretty balanced. It's just 1 carbon and 2 of the oxygens are going to stay pretty straight chained. But it said asymmetrical, it said unbalanced. That's the trick. You need to remember water has that bend shape. That is the one you're looking for. Water being a kind of L-shaped thing with the corners, that's the one that's going to make sense. And if you forget that, if you drew water like this with HOH straight across like that, you may get to the point where you're saying, well, I don't get what happened here. None of them look right. None of them look asymmetrical. They all look like they're balanced. Something's off. I'm forgetting something. And then when you stop and think about it for a second, say, oh, wait a minute. We talked about water being polar because polar things dissolve in water. Non-polar things don't dissolve in water. That's right. I forgot that. It must be the water after all. So that's the one it's going to look like. That's the one that's going to have that bend shape like that. Next one. I2 turns into I plus I. So look what's happening here. You've got a molecule of 2 I's together, and then it looks like it's splitting into 2 I's that are separate from each other. Now let's look at the options. Every option here says some combination of either energy released or energy absorbed, and bond is broken or bond is formed. Well, look at what happened here. You got the I2s, and then they break into 2 separate I's. So obviously a bond was broken. So I'm going to get rid of anything that says bond is formed. I'm going to get rid of choice 1. I'm going to get rid of choice 4. Now we're down to, is energy released or absorbed to make this bond break? The I's like being next to each other. They like being attached to each other. They like being stuck with each other. They like being bonded. If you want to break them up, you need to use energy to make them split up. You need to put energy in. They need to absorb that energy. You need to force them to go apart from each other. So energy is going to be absorbed. So I'm going to cross off anything that says energy is released. And all we're left with then is choice 3. They are stable and they are happy. You need to give them extra energy to get them to go apart from each other. It's not a perfect analogy, but it's sort of similar in how we think about things melting, right? You've got a solid, those solid molecules are all packed tightly and nicely together. They're all holding on to each other really well. If you give them energy, you give them heat. Now you put that energy in, they absorb that heat energy, and now they split apart from each other. It's different level. It's not really breaking bonds. It's just moving things apart from each other, but it's the same kind of idea. 15. Electronegativity difference between the atoms in a molecule of HF can be used to determine what? What do we use electronegativity differences for? Electronegativity is the attraction for electrons. It's things holding on to their own electrons. It's how much they want to attract electrons from somewhere else. And we use the electronegativity numbers to determine polarity. It's, are they really similar to each other where they're all holding on to the electrons with the same kind of strength? Is one side holding on to electrons more or attracting electrons more? Just got to remember how that works. It's electronegativity determining polarity. That's where we had the 1.7 rule. If the electronegativity differences between two elements are essentially none, if it's like 0 up to about 0.3 or 0.4, that's a really non-polar bond. If it's a little bit different, if they maybe are around 1, 1.2, something like that, it's a reasonable difference. They're not exactly the same, but they're not a crazy big difference from each other. That's going to be more of a polar covalent bond. And then if it's just above 1.7, they're not even sharing electrons at all. They're completely different. They're being transferred. That's ionic bonding. 16. Which sample of matter is classified as a mixture? Well, you don't need to know any of these things. You don't need to recognize any of these molecules, know anything about them. I'm just looking at right here. It says solid. This one says it's a liquid. That's a little L. This one says it's a gas. As soon as I see that AQ, that's my answer. AQ just means something's dissolved in water. That's a mixture. It's just two things put together. This is just a solid chunk of NaCl. This is a liquefied, melted down form of CH3OH. This is a sample of SO2 that's been heated up enough that it's a gas, or whatever you did to it to make it a gas. And this right here, KNO3 with the AQ, that means you took that KNO3, you dissolved it in water, and that's your answer. Number 17. At STP, which property of tungsten remains the same for all samples of tungsten? At STP, which is different. So standard temperature and pressure, what's always going to be the same? If you had 2 samples of this metal tungsten, if you had 1,000 samples, whatever, they don't have to be the same mass. You could just have a different size piece, a different weighted piece. You have cut it a different shape or whatever. You don't always have to have exactly the same mass of something. That's obvious. Same thing. If you have a smaller piece versus a larger piece, your surface area is going to be different. So that's not going to be your answer. Thermal energy. How much heat does it have? Even if you have them at the same temperature, a smaller piece is going to have more heat energy in it than a larger piece has, just because there's more stuff there. So it's not going to be thermal energy. But density is always going to be the same. Density is on that table in the reference table, and we can use it to identify different elements just because they always have the same density. And I'm pretty sure I just put my answer sheet over the microphone on the tablet as I was answering the last question or two. So hopefully nobody got messed up, and hopefully if the microphone did cut out for a second, it's back now, because I'm pretty sure it was only the previous question when I realized my answer key was off to the side. All right, number 18. An element is composed of atoms that must have what? What determines what an element is? And that is just something we have been talking about pretty much all year long. Atomic number is what determines what the element is, so I'm not even going to go through the other choices. Proton number is what determines the element, so atomic number is what determines the element. If they are the same element, they have to have the same atomic number. 19. If you don't know that, you're probably not watching this video. Compared to a 2 molar aqueous solution of Ki at 1 atmosphere pressure, water at also 1 atmosphere pressure has what? All your choices have some combination of either lower or higher boiling point and lower or higher freezing point. This is where boiling and freezing point change when stuff is dissolved. If you have just a plain sample of water, we've got water. I'm going to try to move this paper a little bit. It keeps kind of curling up here. I think the camera's maybe not catching it. But if you have regular water, it will freeze at 0 degrees Celsius and it boils at 100 degrees Celsius. That's just property of water. We know that, hopefully. If you add anything to it, it's not pure water anymore. So if you dissolve a little bit of salt, it changes the properties a little bit. If you dissolve a lot of salt, it changes the properties a little bit more. If you just keep adding salt forever and ever and ever, and eventually it kind of uses up all the water, now it's just salt. You keep moving more and more in the salt direction, the more and more salt you add to water, or anything else you're adding to the water. But it moves away from its water-like properties. So the more and more stuff you add to it, you'll have the boiling point go up a little bit. We call that boiling point elevation. So maybe now instead of the water boiling at 100 degrees when it's pure water, now if you add something to it, now maybe you have to get up to 102, 103 degrees to boil instead. And the freezing point drops down. We call this freezing point depression. And now again, instead of maybe freezing at 0 degrees, you have to get it down as cold as -2 or -3 or -4 degrees to get to actually freeze. So this is different utilizations, different things we use for it in life. But you have boiling point going up, freezing point going down. Essentially, everything just moves away from that middle point where they normally are. They kind of move in opposite directions. So I'm going to find a boiling point being higher. So I'm going to cross off lower boiling point in these first two options. And I'm going to cross off, I'm looking for lower freezing points. I'm going to get rid of higher freezing point and higher freezing point. And it looks like the only option I have left is 3. Boiling point is going up, good. Freezing point's going down, good. Those are colligative properties, where the amount of stuff dissolved changes the properties of a solution. Which statement describes the particles of an ideal gas based on kinetic molecular theory? Ideal gases are these gases that are kind of theoretical. In perfect situations, how do we want gases to behave? It's the way we picture gases behaving, even though we know it's not totally accurate, just because it's easier for us to picture them as a model. So they're just bouncing around, lots of energy, not slowing down, never doing anything weird. Let's go through our options. Do we think of gases having attractive forces between them? We don't. I'm going to cross it off. We know they do have a little bit in real life, but we don't imagine that. We don't try to focus on that. Particles move in random, constant, straight line motion. That is going to be our answer eventually. The particles collide, increase in total energy of the system. We don't imagine that energy is going to increase as stuff hits each other. If anything, we would think they maybe slow down as they lose energy. We know how that works from real life. And fourth choice, the particles are separated by distances that are small compared to their sizes. We don't imagine gas particles to have small distances between them. We know they're really far spread apart. We've been drawing those pictures since like probably the third week of school, so that's not going to make any sense. They don't have small distances, so yeah, 2 is our best option. Particles in random, constant, straight line motion. Think of that old Windows screensaver, just the thing bouncing back and forth in some kind of container. That's what we want to think of and picture for gas molecules. 21. Chemical reactions are most likely to occur when reacting particles collide. How? It's reminding us that they have to hit each other. Well, how do they have to hit each other? They have to hit each other with the right positioning, and they have to have enough energy. Well, that's going to be the first choice right there. Proper energy and proper orientation. This has nothing to do with ionization energy or symmetry of molecules or anything. The mass doesn't matter. The volume of it doesn't matter. How many valence electrons? Nope, it's choice 1. You have to hit each other with the right positioning, and you have to have enough energy. When I had the marker caps, if I wasn't lining the caps up with the markers, wasn't going to happen, but they were not going to go together. And once I had them lined up, if I wasn't pushing with enough force to get them to snap together, also was not going to happen. 22. At STP, a 2-liter sample of nitrogen gas and a 2-liter sample of oxygen gas have equal. We had a question just like this last week. We went over it on Thursday on the, was that the 2025 January test, I think it was. It was, I think, a little bit later on the test. It was worded a little bit differently. It was asking for something different, but it was the same idea. Avogadro, the bird guy who talked about the moles, he told us this hypothesis of his, that if you have multiple samples of gas, you can measure their temperature, their pressure, their volume, and their number of molecules. And if you know these things, you can tell stuff about something you don't know. So if we know that they have the same temperature, pressure, and volume, they will also have the same number of molecules. If we know we take the exact same number of gas molecules and put them into the same size of container and raise the temperature to the same temperature, our pressure is also going to be the same. Basically, pressure, temperature, volume, number of molecules. If any 3 of those things are the same, the 4th one will also be the same. So it's telling us we have 2 samples of gas, a 2-liter sample of nitrogen, a 2-liter sample of oxygen. So right there, our volume is the same, 2 liters of each. It's telling us at standard temperature and pressure. So the temperature and pressure are the same. We know 3 of the 4 are the same. Now the number of molecules will also be the same. Right there, choice 2, number of molecules. That's also going to be equal. That's what we were looking for. Just, you have to be given that. It's always going to say something about STP, because that's like kind of hidden information. It gives you 2 bits of information in one shot. STP will tell you same temperature and same pressure, so that gets that information out there, and then it'll either say, here's the 2 things that have the same volume, you got to choose the answer that says same number of molecules, or it might say you want them to have the same number of molecules, same whatever, and you have to find in the answer choice the one that's going to be the same volumes matching to. Either way, same idea, choice 2 here. Number 23, we got 7 or 8 more questions in this section, and then I'll end the video, go on to the next one. 23, based on table H. Let's go to table H. As soon as we see the reference table says use table H, I'm going to go to table H. I'm going to grab my reference table, and table H is this guy right here. It's the vapor pressure. We did not see this much this year just because it's such little kind of minimally useful information. Talks about intermolecular forces, talks about vapor pressure when a liquid's trying to become a gas. But let's see what the question says. Which compound has the weakest intermolecular forces at 75 degrees? All right, so this table shows us vapor pressure. So at different temperatures, it lists temperature down here, and then it shows these 4 liquids and shows their vapor pressure, essentially how strongly they're trying to push up to enter the gas phase. How much of an effort are they making to go from being a liquid to being a gas? So if you have, what's that for, weak intermolecular forces, I think it said? Yeah, what's the weakest intermolecular forces? If you have really weak intermolecular forces, the liquid molecules are not holding on to each other very strongly. If they're not holding on to each other very strongly, they have weak intermolecular forces, that means they're able to make a pretty good push up to become a gas. We'd expect a stronger push into the gas phase, a stronger, higher vapor pressure, because they're not holding on to each other well in the liquid phase. So it said at 75 degrees, which one has the weakest intermolecular forces, means at 75 degrees, which one's going to have the strongest vapor pressure and pushing up. So let's just see at 75 degrees, well, really at any temperature doesn't really matter because they're always in the same position. They don't cross over each other at all. But at 75 degrees, we can go up, and then what the strongest vapor pressure is going to be this line right here for propanone. That's going to be our answer. It has the strongest vapor pressure, the strongest push up to become a gas, because it's not holding onto itself really well in the liquid phase. Weak intermolecular forces. 24. Which term identifies a force of attraction that exists between molecules of water? Well, we just talked about intermolecular forces. Those are the attractions between molecules. This answer is asking about a type of intermolecular force, and you just have to remember that hydrogen bonding is what water does. That's just something water always has, kind of associated with it. Metallic bonding is just the electron movement and what's holding a metal together inside a piece of metal. Ionic bonding is metal with nonmetal. Covalent bonding is non-metal atoms holding together. But hydrogen bonding is attractions between molecules. It's not saying what's going on inside a molecule of water. So it's not saying what's holding this H to the O or this H to the O. It's not saying what's holding the water molecule together. It's saying if you've got another water molecule over here, how are these two neighboring water molecules attracting each other, holding on that way? That's hydrogen bonding. That's an intermolecular force. 25. Which process results in an increase in disorder? An increase in disorder, that's an increase in entropy. It means it's getting more spread out, it's getting more random, it's getting more messy, whatever. If I look at the choices here, they're all states of matter changes. Condensation, freezing, it's all solid, liquid, gas changes, back and forth, physical changes. So which one's going to increase the disorder? Which one's going to increase the randomness? Which one's going to spread pieces out and make them less orderly? Well, condensation of water vapors, when a gas turns into a liquid, so they're actually getting closer together. They're getting more kind of condensed. That's not going to be our answer. That's not going to increase the disorder. Freezing of liquid ethanol. Freezing is liquid going to solid. That's definitely not going to increase disorder. It's going to have everything nicely structured. They're coming together, packing in tighter. Sublimation. Sublimation is like dry ice. In this case, it says iodine. Sublimation is when a solid goes to a gas. That looks pretty good. Solid going to gas, that should definitely increase disorder. Let's just double check our last answer choice. Solidification. Well, solidification is just freezing. It's becoming a solid. So that's going to be the same as choice 2. It's going to be liquid going to solid. So that's also not going to be our correct answer. Sublimation, solid going to gas for sublimation. That is going to be the best answer. That's increasing disorder, definitely. 26. Systems in nature tend to undergo changes that result in every year it's on the test. I've been telling you that since like November, whenever we saw it the first time. I think the test we saw the other day was question 22 or so. It's 26 this time. It's always right around this place. You're looking for an increase in entropy, that randomness and that disorder. We just saw in number 25, so an increase in that delta S. And you're looking for a decrease in delta H, a decrease in energy, a decrease in heat, decrease in enthalpy. So looking at our choices here, it's not going to be an increase in both because they're going to change differently. It's not going to be a decrease in both. You want to be different, doing different things. But it's going to be a decrease in energy and increase in entropy. Things naturally get more random and heat naturally spreads out. Hot food will get cold because heat will move out of it from hot to cold in the environment. And things naturally kind of get more messy. They naturally get more messed up and disorderly and random as time goes on. So choice 4, that will be on every Regents forever. 27. What is the general formula for the homologous series that includes ethyne? Reference table question. We haven't had a lot of them. Homologous series and general formulas. That is on table Q. That is the organic homologous series chart. And it says the homologous series that includes ethyne. So you just notice that little ine at the end there. That's talking about these guys right here. And I mean, it actually says ethyne on the chart. You don't even have to figure out which is which. Ethyne right here, it's a YNE ending. It's a triple bond. That's the alkynes. So this is the general formula right there. CnH2n-2. Whatever number of carbons you have, whatever that N happens to be, you're going to have twice that number minus 2 for your number of H's. So like in this picture right here, it shows 2 carbons, so 2 is our N. So if it's N equals 2, that would be C2. And for the H, it's 2N. 2 times 2 is 4. Minus 2 is again 2. So we have 2 H's. But that's the general formula. It's asking for the general formula, CnH2n-2. And we just have to choose choice 4 right there. Nice, and we can just go look stuff up. Given this equation, looks kind of like one we had before. 2KIs plus F2 goes to 2KF plus I2. When 2 moles of electrons are gained by fluorine, how many moles of electrons are lost by iodine? This goes back to, I think it was the last question on the first page, right? Yep, if we look at number 9 on the first page, which quantity is conserved in all chemical reactions? Charge has to be conserved. So right here, charge has to be conserved. If we're losing 2 electrons from something, how many electrons are gained by somebody else? It says we're gaining 2 moles of electrons, so the number of electrons lost by somebody else has to also be that same 2 moles. Nothing to figure out, no math to do. It's just you're losing this many electrons over here, you have to gain that same number of electrons over there. Has to balance out, has to be equal. 29. Which compound is an Arrhenius base? Everybody always forgets this word Arrhenius. That's just the guy's name, the guy who told us about acids and bases. Any question about which is an acid or base, just go right to your chart. If you remember that acids have H in the beginning, if you remember that bases, you look for OH at the end, that's great. You can just find the answer right there. If you remember, bases have the OH. That's the only one with an OH. But if you forget, go to your reference table because they're pretty much always on here. Most times when you have a question like this, which one's an acid or which one's a base, it's going to be on the reference table. You don't have to figure it out. You don't even have to look here and say, oh, look, they all have OHs. Let me find, and there'll be like an answer that has an OH that you haven't seen yet. No, it's right there. CaOH2. They literally give you the one that's on there. So CaOH2 is the only one on the base chart. That's your answer. And 30. Which statement describes a benefit of fission? Fission is nuclear reactions. It's a bigger, larger isotope mass, or nucleus breaking down to smaller pieces. It's saying which is a benefit of this. So we often think about nuclear reactions as being dangerous or not being the best things for us, but which is actually a positive. So you're looking for some kind of positive answer. Fission produces nuclear power. It does. So that sounds pretty good. I mean, that's something we can use. That seems like a reasonable answer. Fission increases the possibility of nuclear accidents. Well, whether that's right or wrong, that wouldn't be a good thing. So that's not a benefit at all. Hopefully everybody realizes that would not be a positive. Fission increases the possibility of biological exposure. Again, we don't want to be exposed to nuclear radiation or anything, so that would not be a good thing, whether it's right or wrong. Fission produces waste products that need long-term storage. Also, not a great situation. So even if you forget exactly how this works, giving us nuclear power, that is a good thing. We do use it for energy. If it's done correctly, it can be safe. That is a benefit, and that's something we can choose for there right there. Okay, so that is the first 30 questions. The first section of this test is 30 multiple choice. You can see they were kind of straightforward questions, a couple just definitions, a couple we had to look up something in the reference table pretty easily. I'm going to cut this video off and start the next one. That is your first section. The next one will be 20 additional multiple choice questions, a little bit more involved, a little more maybe math or reference table type stuff to do. And then we'll have the last 35, which were the short answers. So I'm going to pause this here and we'll get to the next one.